All right, pharm students, let's talk about one of the biggest headaches in drug formulation, mixing things that absolutely refuse to mix. Today we're going to get hands-on with a key piece of gear designed to solve that problem, the Silverson Emulsifier. This is essential stuff, so let's jump right in.
You know the old saying, right? Oil and water don't mix. It's a fundamental rule. But in our world, in pharmacy, we have to break that rule all the time. You can't just shake them up and hope for the best. To make those smooth, effective, and safe products that patients need, you gotta have some serious hardware that can force those ingredients to play nice.
So, here's how we're gonna break it all down. First, we'll look at the challenge itself. Then, we'll get into the guts of the machine, its anatomy. After that, the real magic, how it works. We'll see where you'll actually use this thing, and finally, we'll give it a fair review, the good and the bad.
Okay, first up, the unmixable challenge. I mean, we've touched on it, but let's be super clear. Getting things like oil and water to stay mixed isn't just tricky, it's absolutely critical. Because if your emulsion breaks, you're looking at separated ingredients, which means the dosage is all wrong. That's not just ineffective, it's downright dangerous.
So how do we solve it? Well, the answer is basically controlled violence on a tiny scale. We use something called a high shear mixer. And today, we're talking about a real classic, an industry workhorse, the Silverson Emulsifier. This machine was literally built to tackle this exact problem with pure power and precision.
Okay, let's pop the hood on this thing. We're getting into the anatomy of the emulsifier. To really get how it works, you've got to know what's inside. Every single piece has a crucial role to play.
So check out the core components. You've got your tough stainless steel body, right? But the real action is in that high-speed rotor stator assembly. Think of it like this. A super powerful motor spins this vertical shaft with sharp blades on it. That's the rotor. And that rotor spins inside a stationary cage with tiny little holes. That's the stator. This whole setup, the mixing head, is where everything happens. It's the heart of the machine.
And when I say high speed, I'm not kidding. We're talking up to 10,000 RPM. That's insanely fast. It's this mind-boggling speed that creates the sheer, raw force we need to literally rip these liquids apart and smash them together.
You see, the rotor and stator work together perfectly. The rotor spins like crazy, and that creates this powerful vacuum that sucks both liquids right into the mixing head. Then that same force blasts the mixture out through the tiny perforations in the stator. It's this violent process that guarantees you get a super fine, totally uniform mix.
All right, so we know the parts and we know it's fast, but what's the physics behind it? What's really going on in there at a microscopic level? Let's talk about the power of shear. This is the secret sauce.
The number one principle here is shear. Here's a simple way to think about it. Take a deck of playing cards and just slide the top half off. That force between the two sliding halves, that's shear. Now imagine that force but magnified 1,000 times, with blades spinning at incredible speeds, literally tearing globules of oil into microscopic little bits. That is the awesome power of shear.
But wait, there's more. It's not just about shear. We also have impact. As those droplets are getting fired out of the stator at warp speed, they smash into each other, they smash into the blades. It's like a tiny, chaotic demolition derby in there. This just helps to pulverize anything that the shear force might have missed. So let's walk through the whole process. Step 1, you stick the mixing head right into your liquids. 2, you hit the power and that rotor starts sucking everything in. 3, inside that head, you get that intense 1-2 punch of shear and impact just breaking everything down. And here's the key. It doesn't just go through once. The mixture gets circulated over and over again, getting smoother and finer each time. And finally, when it's perfect, a stable emulsion gets pushed out.
Okay, that's the how. Now for the so what. Why do you, as a future pharmacist, need to know this inside and out? Because this isn't just theory. This is about the actual products you're going to be making for the rest of your career. From the lab bench to the pharmacy shelf, this is where it all happens.
And the uses are, well, they're everywhere. Think about it. Pretty much any emulsified cream or ointment you can name, a high shear mixer was probably involved. Dispersing a solid into a liquid for suspension? Yep. Mixing up thick, gooey gels and syrups? You bet. Even making things like oil-based herbal products or adding flavors to medicines. This machine does it all.
This really says it all, doesn't it? From the most basic creams to really complex suspensions, a machine like the Silverson is an absolute cornerstone of how we make medicines.
All right, time for the final verdict. Because look, no tool is perfect,
right? A huge part of being a good pharmacist and a good scientist is knowing the strengths and the weaknesses of your equipment. So let's get real about the pros and cons.
So on the pro side, it's fast. Man, is it fast. You get fine, stable emulsions in no time. It's also super versatile, and it works for small lab batches or huge industrial ones. Plus, it's easy to clean, which is always a bonus. But there are downsides. That speed takes a ton of energy. And more importantly, it generates a lot of heat. If you're working with a delicate drug, that's a huge red flag. It also struggles with things that are super thick, and yeah, it can be pretty loud.
And this right here is the whole point. Anyone can learn to turn a machine on, but a skilled pharmacist, a real formulation scientist, knows when to use it and when not to. It's about understanding these trade-offs and knowing how to work around the limitations to get the perfect result for your specific drug.
So I'm going to leave you with a question to chew on. A real-world problem. You know this machine gets hot. So what would you do if you had to make an emulsion with a very expensive, heat-sensitive drug? How would you adapt the process? How would you protect that ingredient? Really think about it, because solving problems like that, well, that's what being a pharmacist is all about. Thanks for tuning in.